Okay, we'll go ahead and get started. So this is the live stream for Wednesday. And again, it's being recorded so that I can upload it onto YouTube after it renders. That will be later tonight. So a couple announcements here. Your exam 3 will be through Canvas, Wiley Plus. You have to download this browser, and the information to do that is in Canvas. Once you do that, I will upload, make an announcement in Canvas about the password that you have to enter into that browser to access the exam. The exam is going to be open, I believe, from 7 a.m. to 7 p.m. on Monday. You will have 75 minutes to complete it, and then it should score automatically so that you see your score uploaded right into Canvas when you're done. So your homework 8, quiz 3, and exam 3 bonus are all due Monday through Wiley Plus as well. If you haven't started that, I would definitely encourage you to start that as soon as you can. Again, try to do a couple problems every day rather than waiting till Monday morning, because it's going to be a lot of work. So the exam is, as Harley mentioned there in the chat function, it's set from 7 a.m. to 7 p.m. on Monday. You can open it whenever you're free, but once you open it, you have 75 minutes to complete it. With this software, you are not allowed to leave and come back. So make sure you have 75 minutes free to start and finish it. Again, it will be 30 problems. It's worth 120 points. And so that's exam 3. Again, if you have any questions, throw in the chat or unmute your mic and ask, and we'll try to make sure everyone's on the same page. So what I thought we would do today is some problems first, and then we'll get into the Claisen reaction, the Michael reaction, and the Robinson annulation. So it's pretty ambitious. We'll see how far we get. But I'd like to start with problem 2175. And again, I apologize for this being blurry, but it's the best I have right now. It's sort of janky, but it is what it is. So this problem from the book 2175 says, draw a reasonable mechanism for the following transformation. So we're given this ketone that has saturation between the alpha and beta carbons. So again, there's alpha, there's beta. So this is called an alpha-beta enone. And what that means is between the alpha and beta positions, there's an alkene, and they're right next door to a ketone. That's where the ONE comes from. So this molecule, when treated under these conditions, gives cyclohexanone plus 2 propanone. So the question is asking us to draw a mechanism. And basically what this is overall is called a retro-aldol reaction. So if you look at what's the products of this reaction, if you were to go this way, that would be called an aldol dehydration. So the aldol reaction can go back and forth. So this is the product of an aldol, and we're basically just going back to the 2 starting materials. So it would be a cross aldol. We have one ketone reacting with another. So how do we get back from the condensation of these 2 to that? So again, the product of an aldol reaction is a beta hydroxycarbonyl. So what first is going to happen here, the sodium hydroxide is going to add to the beta position. So once it does that, we're gonna push arrows this way and basically form an enolate. So even though I mentioned we'd get to this a little bit later on today, this is actually, this first step is called a Michael addition. So that's another reaction we'll look at. A Michael addition is the addition of nucleophile to the beta carbon of this type of system. So we'll explain more about why it adds there, but moving forward with this, at this point, we've formed essentially, this should look familiar to you now. This is called an enolate. And what we can do under these conditions is protonate the alpha position using water. So here's our alpha position. There's that beta position. We're going to protonate alpha. That restores the carbonyl. So alpha, beta. So this is the most familiar thing to you at this point of being a beta hydroxycarbonyl. So that is an aldol product. So at this point, we're under basic conditions. We can use the base to deprotonate that hydrogen. The pKa of that, again, alcohol is about 15 to 16. We're going to deprotonate that. And at this point, this step is the retro-aldol. So once that deprotonates, these electrons collapse to do an elimination. So we reform that pi bond. We break the alpha beta bond. And what we're doing is forming the enolate of the cyclohexanone. So I always like to show the counter ions balancing the charge so we can keep track of the lone pairs. So once we do that, so again, we're deprotonating, we're eliminating here, we reform that pi bond. This forms the enolate. So there we've formed the ketone, the 2-propanone. Now to get to here is a matter of just proton transfer. So this will collapse. It will attack the water to do that proton transfer. That's how it gets that second alpha proton there. So with this question, what you need to realize is that the aldol reaction can basically go in reverse back to its two constituent carbonyl components. That's called a retro-aldol. This product basically is a aldol dehydration. So again, what's happening from the beta hydroxy position is just elimination of the water. That's how you get the double bond there. So any questions on this before we move on to another problem from the book? Okay, I don't see any in the chat, so we'll move on to the second slide here. And this will be problem 2181, where we're given the following ester. So just to name this ester, you always name the alcohol portion first. So that's ethyl. Then we have 1, 2, 3 carbons, so that's a propane derivative. So that would be ethyl propanoate. So when we name esters, you name the alcohol moiety, then the acyl moiety. You drop the E of the parent and add OATE. So we're treating this with LDA in step 1. So remember, LDA has the following structure. The L stands for lithium. The DA is diisopropyl amide. So this is a pretty strong base. So we're forming an ester enolate in the first step. Then we're treating with 2-propanone in the second step. In the third, we're doing an aqueous workup. So what we're going to do is show each of those, and then we'll draw the final product as well. So here we have the carbon 2 here is the alpha carbon. So again, with esters, there's only one alpha carbon. You only run into the situation of 2 alpha carbons with a ketone, so that's really what you have to know. So the base is going to abstract one of these protons. So the base abstracts, that's that arrow. That's the formation of the enolate. With LDA, this arrow is one way. So right, LDA is kinetic. That means there's no back and forth. It's forming the enolate in 100%. So this is a lithium. A lithium enolate of an ester. I'm not showing the byproduct of this acid-base reaction. Maybe I'll just draw it so you can see. So that's the conjugate acid when that deprotonation event happens. So this is the ester enolate. So there's your alpha position. Again, this is a nucleophile. It's reacting with this molecule, which is acetone or propanone. This is your electrophile. So this will collapse. The reaction occurs at the alpha position to the carbonyl carbon. So that's a nucleophilic addition. Again, the oxidation state goes from 2 to 1. So there's your alpha. Here's your new beta position. The oxidation state has been reduced. So the last step, H3O plus, is just a proton transfer. So there's the product that you would get with an ester enolate acting with a ketone. So in the chat function of this product here, how many stereoisomers would be formed? Maybe you can just write in a number in the chat box. 4, 3, 4, 4. So the people that wrote 4, maybe you can write a brief explanation or unmute your mic and explain how you're getting 4. So Ireland, can you? Ireland says there's 2 stereogenic carbons. Trevor says there's 1. So is there 2 or 1? So if we're looking at this, again, we have a beta hydroxyester. So Ireland sees the issue. The beta carbon, this is not a stereogenic carbon because you have methyl and methyl. Only the alpha carbon is a stereogenic carbon. So we have 2 to the 1 that equals 2, and those would be R and S. So again, since we're in a unique situation here with Trevor sees as well, with the virus, you're not taking the ACS final. So, you're going to be taking the final online. It's going to be similar to what you're going to do for exam 3. But some of you, again, are taking pre-professional exams, and it's good to review this stuff. So you're going to get a 1-to-1 mixture of this. So a 1-to-1 mixture of R and S, that's called a racemic mixture. And so of that, the optical rotation of that's going to be 0 because the R will cancel out the S. What else can I say about this? Any questions before we move on to another one? Okay, so we'll do another one. This is going to be 2199. And it says, draw a plausible mechanism for the following transformation. So we're given this alpha beta unsaturated ketone with base, water, and heat. That molecule is transforming into the following. So there's alpha, there's beta. So notice here in the starting material, you have a hydrogen. At the alpha position, the beta carbon has an ethyl group. In the product, alpha and beta both have methyl groups. So I apologize for the blurriness of this. I don't know if me moving this closer will help. So we're going to write the mechanism. And in doing this type of mechanistic problem, it's easy to sort of invent things that you've never seen before. And I think what organic chemistry will really help you with in terms of your thought process, basically you can't make shit up. You have to abide by known mechanistic reasoning. So this type of problem, if you were to do it on your own, I would think there would probably be a lot of confusion about how this H somehow becomes a methyl. And actually, what this is a retro-aldol aldol is what we're going to look at. So an alpha beta unsaturated ketone is an aldol dehydration product that can undergo a retro-aldol. And what that essentially is going to do is clip the alpha beta bond. And we know that the beta position of an aldol reaction is a hydroxy. So that's going to unfold into basically one carbon chain that has a carbonyl there and there. Then that's going to undergo an aldol reaction basically between this alpha carbon and that carbonyl. So essentially what we're doing is a swap of the aldol. So let's just get to it. Let me first show you why the hydroxide adds to the beta position. So in a resonance form of this, if we push arrows like that, this is a resonance form. We can reform the pi bond here, put the electrons on oxygen. So the beta position now has a plus charge. So again, that's a resonance form. Hydroxide in this case will act as a nucleophile to add to the beta position. So nucleophile reacting with electrophile. So this is sort of now resembling an aldol. This is an enolate, which we can protonate with water. So notice we started with one hydrogen, it's now getting two. So bear with me, this mechanism is going to get sort of long. So at this point, this is your aldol product. So what we're doing now, going this way, is a retro-aldol. So here's aldol, this is aldol dehydration. So I'm just going to erase that. I want to actually draw that H out because the hydroxide now is going to act as a base. To deprotonate, we're going to do an elimination between alpha and beta. So we deprotonate, this eliminates, we break alpha beta. Those electrons basically form an enolate at this position now. So let's draw these H's in. So what happens here, we have this enolate, this will collapse to protonate at that alpha position, giving us back to our methyl group. So now we have these three H's. So that's the complete retro-aldol. to that position. Now what we have to do is the second aldol to get to here. And so I'm going to just use my red pen here. 3D. So this is a methyl group. That's a methyl group. So that just by identifying that, we can look at this. Here's a methyl group. There's a methyl group. So those have to remain unchanged getting to this product. So that helps us figure out, because in this molecule, we have alpha, alpha prime, alpha double prime, alpha triple prime. So we have all these alpha carbons, and you say, how do I decide which one gets deprotonated to act as the enolate to attack the electrophile? So because these two remain unchanged, we're forming a 5-membered ring here. It's this alpha position here that has to attack that carbonyl. So if we count 1, 2, 3, 4, 5, that will form a 5-membered ring and leave those methyl groups intact. So let's go through. We have these two H's. We're going to have hydroxide deprotonate one of them. And again, that's forming an enolate. So really another thing what this problem is about is, you have to understand that the way things are sometimes drawn, they can be rotated or flipped, and that may be confusing about how things are oriented. So we've done this deprotonation of that alpha position. This is now our enolate nucleophile. Here's our electrophile. So let's number. There's 1, 2, 3, 4, 5. So let's just draw a 5-membered ring. Then I'm going to number it. 1, 2, 3, 4, 5. So when this collapses, 1 attacks 5, so that's the bond we formed. 5 has a methyl group, and now we've reduced that oxidation state. 4, 3, 4, 3 are both methylene. This collapsed down to form a ketone. 1 has an H and a methyl group. So now what do we need to do? You can see the methyl groups are intact. Just use the red dot to show how they track through. We need to protonate this alcohol with water. So that's a proton transfer. Here's our aldol product, a beta hydroxycarbonyl. Now the remaining step to get from here to there is an elimination of water. At the alpha position. That's where this heat comes in up here. This is an E2 elimination. We have an abstraction of this proton. We form the alkene, and then hydroxide eliminates. So red dot, red dot, red dot, red dot. So from this aldol product, we basically open that ring up to get to the starting material of this second aldol here. So at this step, we do an aldol and then a dehydration. Any questions before we move on? So it's 1:30. We got about 45 minutes left. And so what I'd like to do now is continue on with the Claisen reaction. So the Claisen reaction or Claisen condensation, the electrophile is at an oxidation state of 3. It gets reduced to 2, which forms a beta keto ester. So I'll just continue on with the mechanism that we started with last time in terms of a self condensation. So if this compound, this ester, ethyl acetate, undergoes a self-condensation, you end up with ethyl acetoacetate. It has 2 different alpha carbons here and here. These are pretty acidic with a pK of 10. These are about 20. So because this is at oxidation state 3, that's the highest priority functional group. This is at oxidation state 2. So we're forming at this point a beta keto ester. So when you run this reaction, as I mentioned before, you have to use a base that's the same as that alcohol of the ester. So that base is run in sort of that alcohol, but these things have to match. Then you have to do an aqueous acidic workup. And so I need to explain that through the mechanism. But the first thing we're going to do, I'll show one alpha hydrogen here is an acid-base reaction. So you've seen that before. This is going to form an ester enolate. So this is the nucleophile. And since it's a self-condensation, it's going to react with another molecule of itself. This moiety is the electrophile. So the Enolate Collapse so you saw this mechanism in the last module. This is nucleophilic acyl substitution. We are substituting this O-ethyl for the rest of this molecule. So this oxidation state 3 gets reduced to 2. We form the bond between that bond between alpha and the new beta. This collapses to do an elimination. And so this is where you really have to be mindful, like why I'm talking about this acid being here. At this point, you form ultimately the final product, but because you're still under basic conditions, the ethoxide that was eliminated will deprotonate these now very acidic alpha protons. So once this happens, notice these arrows are equilibrium. At this step, it's one way. So the reaction will sit at this enolate until you add the acid or adjust the pH. So all that's happening with that is a proton transfer. So you actually can end up with a neutral molecule. Again, the Claisen is the only one that's sort of like this. While you are forming that product, you have much more acidic hydrogens now that will stop at this enolate until you adjust the pH. So the Claisen will always give you a beta keto ester. So maybe let me sort of in this, I don't know, area here. So these were the three type of reactions we saw with enolates. An alkylation, the starting electrophile is at 1. In the product, the beta position oxidation state ends up at 0. In the aldol, you're starting an electrophile of 2. It ends up as 1, so that's a beta hydroxycarbonyl. The Claisen, your starting electrophile is 3. It's ending up as 2. So this is a beta keto carbonyl. So overall, these reactions are all reductions, 1 to 0, 2 to 1, 3 to 2. And then the nature of the functionality can sort of tell you what overall the name of the reaction was. So just like with the aldol reaction, if you want this self-Claisen product, that's fine, but sometimes you don't want it. So what you can do are crossed Claisens. So let's look at a cross Claisen. And it pretty much has the same complexity issue as the crossed aldol. So we'll look at crossed Claisen, and then we'll examine ways that you can get around the issues with forming so many products. So we'll do cross condensation. And we're basically just going to use the same molecules that we did for the aldol, except now they're at a higher oxidation state of 3. So we're going to use ethyl acetate plus ethyl propionate. So both are ethyl, so we're going to use sodium ethoxide in ethanol. And then we have to do an aqueous acidic workup. And so again, when you're asked to predict how many products there's going to be, the best way to solve this is just to be logical about things. So let's do, we'll set up some columns here. We'll do self, cross, cross, self. In this column, we're going to show the electrophile. This column will show the nucleophile or the enolate. And then we'll draw the products over here. So if we're looking at what we just saw in the prior slide, the self-condensation of the ethyl acetate, the product of that, here's your alpha, there's your new beta, and again, a Claisen is a beta keto ester. So we just saw that from the prior slide. That was the self-condensation of this. Let's look at the self-condensation of the ethyl propionate down here. The electrophile is just going to be the molecule itself. The nucleophile is the enolate. So here's alpha. This is going to become beta. This is the bond you're forming. So now we form one stereogenic carbon. So the reason we're forming R and S there is based on the nature of the enolate here. So you can have two different types of enolates based on the geometry. Now let's look at the crossed situation. So those were so far in just the self ones, we have 1, 2, 3, 3 products forming. So already this is sort of a mess, right? So the first cross, let's look at this being the electrophile and then the enolate coming from the ethyl acetate. So now here's from everything here on is your beta position. Everything here on obviously is you're forming this bond. So that's the bond you form between alpha and beta. So there's no stereoisomers here. So we have 1, 2, 3, 4. That brings our count up to 4. Now for the other cross, we're going to use this as the electrophile, and then this is the enolate. So just to show you the difference, over here I drew the other geometrical isomer of the enolate. However, for the ethyl propionate, you form both. I'm just showing one. So this product of that crossed Claisen, that's the bond you form. That's a stereogenic carbon. So of the crossed, you have 1, 2, 3 as well. So you end up with 6 possible products if you mix these things together. And again, that's not an ideal situation in chemistry. You really want to run a reaction that forms one thing in 100%. So if you think about, this COVID-19 virus that's going around, one of the treatments for it is hydroxychloroquine or chloroquine. If you look up that structure, it's not terribly hard, but there's ways that you could get different chemicals out of it. And if you're trying to treat a couple billion people, you obviously want the most efficient chemical reactions to make that stuff, and you don't want to be separating mixtures of things. So really, what you want to take away from this is that these reactions can produce a lot of things, and so how can we control that? So just like we saw with the aldol, when we're doing crossed Claisen condensations, so to control the cross Claisen, you want to use electrophiles that do not have enolizable alpha carbons. So what that is basically stating is that these compounds basically have to be the electrophile. So one of them is ethyl benzoate. So there's your alpha position. It's non-enolizable, so it has to be an electrophile. So if you react that with ethyl acetate under the standard conditions, you are going to get some of the self-condensation, so that's unavoidable. But now you can't do any, this can't do any self-condensation, so it's basically this acting as the enolate attacking that. So you're at this point, you've reduced the complexity in terms of the number of products. So another type of non-enolizable substrate would be this ethyl pervalloate. So that's a common name, but again, the alpha position does not have any hydrogens. So these are non-enolizable. So those would be good for controlling the cross Claisen. Any questions on the Claisen? So we'll do one more reaction regarding the Claisen, and then we're going to move on to the Michael addition. So just as we saw with the aldol, there's intramolecular aldol where you form a ring. The intramolecular Claisen is called the Dieckmann condensation. So an intramolecular Claisen reaction has a different name. It's called the Dieckmann condensation, and it forms a ring. So if we look at the following substrate, we have this diester. My computer's falling asleep. Hopefully you guys can still hear me. Sorry about that. So we have this diester, and basically, because it's intramolecular, the enolate and the electrophile are within the same molecule. So this molecule, if you look at it, it's symmetric. You have an alpha position here, you have an alpha position there. So it doesn't matter which one you deprotonate. What you do want to do is first number. So say we enolize from this alpha carbon. Again, you can enolize from that one because they're the same. If we enolize here, this is 1, 2, 3, 4, 5. Form an enolate there. This is the electrophile. So this is a 1, 2, 3, 4. We're forming a 5-membered ring. Let me show you. I'll let you imagine how this enolizes with this base. Nothing new there. So there's the enolate. Here's our numbering system. Because this is intramolecular, the enolate then attacks the electrophile. And again, this mechanism is nucleophilic acyl substitution. So let's draw a 5-membered ring. Let's number that ring. Two, 3, and 4, nothing changes. 2, 3, 4. The action happens at 1 and 5. At 1, there's a hydrogen. Then the rest of this ethyl group. 5, you reduce the oxidation state from 3 to 2. So there's your alpha, there's your beta. This does the elimination. So there's your beta keto ester. Again, because we are under, now this is pretty acidic and we're under basic conditions. That gets deprotonated. And it forms with a one-way street, the enolate. Oops. So again, it sits at this position until we add this acid. And again, that's the final step. It's just a protonation event back to that beta keto ester. So again, a Dieckmann condensation gives you a ring which has the beta keto ester embedded in it. Any questions or comments on the Dieckmann condensation? So in the last, it looks like 20 minutes here, we're going to move on to that Michael addition. And then we're going to look at a special case of the Michael addition and aldol reaction. That's another named reaction called the Robinson annulation. So the Michael addition is an addition of a nucleophile to the beta position of an alpha-beta unsaturated carbonyl system. So let me first preface this with sort of a review here. So this is conceivably the product of an aldol dehydration reaction. There's the alpha carbon, there's the beta carbon. X can be pretty much any functional group we've seen. If it's H, it's an aldehyde. If it's C, it's a ketone. Or we can have esters, amides, etc. What we've seen a lot so far in organic 2 here is the addition of a nucleophile right to a carbonyl. So we've seen that quite a bit this semester and last semester. You think about a Grignard adding to a carbonyl. So that's the new bond formed. This reaction is actually called a 1,2 addition. So again, that's just like a Grignard, addition of a nucleophile to a carbonyl. However, the presence of this unsaturation here can lead to the following resonance form. So maybe I'll show it in red because we've got a lot of arrows going on here. So in a resonance form, the electrons can be delocalized onto the oxygen. So at the beta position, you have this plus charge, the oxygen's then bearing a negative charge. So depending on what the nucleophile is, if it can add 1, 2, or if it's a weaker nucleophile, it can add to the beta position. And that's called a 1,4 addition. Or Michael addition. So one of the things about organic chemists is there's a lot of named reactions. And historically, people in the field will honor the original author of a paper by calling it, since Michael popularized these, Michael is the guy's last name, it's not the dude's first name. But basically, people start referring to it as like an honor. And it's a recognition. I believe, I don't know if Michael won a Nobel Prize, but Robinson surely did. And we'll look at that in a little bit. So it's the addition of a nucleophile to the 4 position. So again, here's your alpha carbon, there's your beta carbon. So this is the bond that we're forming right there. Now, if you look at what remains here, this section here is an enolate. And so the power of the Michael addition, when the nucleophile adds to the beta position, you form this enolate that you can then trap with a second electrophile. So this comes down and it will attack at the alpha position. So if you look at overall what we did from where we started, we're adding a nucleophile to the beta position and an electrophile to the alpha position. So the Michael addition is really powerful because you can do basically what's called cascade reactions, where you take these things and you're doing a lot of stuff at once to build complexity. So what type of nucleophiles are involved here? We're typically going to use weaker nucleophiles. So things like potassium cyanide, neutral molecules like alcohol, such as methanol, neutral amines, methylamine, thiolate anions can be used. Enolates themselves can be used. So enolates are good nucleophiles for the Michael addition. So things over here, how do you differentiate these nucleophiles from these? So 1,2 nucleophiles are basically things like these Grignard reagents. They only do 1,2. Things like alkyl lithiums, things that are really strong carbanions will typically do 1,2. Weaker nucleophiles will do 1,4. So let's take a look at a Michael addition reaction. So we've seen ethyl acetoacetate before. So this thing can form an enolate. We now have an ester that's unsaturated between the alpha beta positions. So if we were to react these two things with sodium methoxide and ethanol, this would form the enolate. So we're doing an acid-base reaction to form that enolate, and this is going to act as the electrophile. So this carbon attacks the beta position. We're pushing arrows then again to form the enolate. So I'm drawing the new bond that's forming right there. Then we have 3 carbons. So this is the new bond. We have 1, 2, 3 carbons. This was the former beta carbon. So under these conditions, this thing will just protonate. So we're going to basically put the proton back here from this enolate and end up with the Michael addition product. So that's a Michael addition. And these can be a little bit harder to spot in terms of, identifying alkylation, aldol, Claisen, etc. Maybe one thing I can point out to those of you that are maybe interested. This part of the molecule, there's a 1, 3, so I'm counting just 1, 2, 3. This is a 1, 3 dicarbonyl. If I start numbering the other chain, 3 prime, 4 prime, 5 prime, we have 1, 2, 3, 4, 5. So the trend is that this one odd relationship in nature, the one odd relationship, 1, 3, 1, 5, 1, 7, that's a natural bond formation. And we really don't have enough time in the semester to get into it, but if you take biochem and you study how things are made through like microorganisms, how they make bonds, it's always this one odd relationship that happens in nature. So a Michael addition just happens to be the 1, 5. So that's maybe a way you can spot a Michael addition is if you have 1, 2, 3, 4, 5, a 1, 5 relationship between the carbonyls. The 1 even relationships like 1, 2, 1, 4, these are called unnatural. And this is what I sort of do in my own research at USM. We study these things to make bond constructions that you can't do naturally. So again, to spot a Michael addition, it's a 1, 5 relationship between the carbonyls. And again, this is the bond that you formed. Any questions on that before we just wrap up with one last topic for today? So I know this is a lot of material, but again, Keep in mind your exam on Monday. Obviously, you can use your textbook. I have no way of verifying if you have people helping you or not. That's completely up to you. You're on the honor system. I would say try to do it by yourself as an accurate reflection of your knowledge learned in the course. But I do want to cover one more named reaction that is important historically, and that's called the Robinson annulation. So the Robinson annulation is actually two named reactions. It's a Michael addition followed by an aldol dehydration. And I think it's important for you guys to at least see this because historically it's been used in the synthesis of steroids. So prior to the 1930s, people knew steroids existed, obviously, but they had never made them in the lab. So the Robinson annulation, which is, again, a cascade of these two reactions, was used to construct part of the carbon backbone of steroid molecules. So it does have a pretty significant meaning in human civilization. So just to give you an idea, this molecule is going to be our nucleophile. So we have a beta keto ketone, beta dicarbonyl. We're going to react it with this compound, which is called methyl vinyl ketone. That's the electrophile. Again, I'm not going to draw all the mechanism out for this. I'll probably post a screencast doing that later. But the first thing that happens is a Michael addition. So here's your alpha acidic carbon here. This gets deprotonated. It adds to this beta carbon. So that's the bond we formed through the Michael addition. So again, we have 1, 2, 3, 4, 5. There's the 1,5 dicarbonyl relationship. This is the Michael product. Now you have a bunch of different alpha carbons. We have alpha, alpha prime, then these over here are the same. So it turns out we can do an aldol dehydration, and the one that's going to be favored is the following. If we count, say here, 1, 2, 3, 4, 5, and it doesn't matter which way we go, 6, that will be 6 as well. We're going to form an aldol reaction between carbons 1 and 6. So this is the new bond we formed from the aldol. Then we're going to do a dehydration of H2O. So that's the dehydration, and that happens from an E2 reaction. And overall, the Michael addition followed by the aldol gives you this. So what we've done is we've added these 4 carbons onto these 2 right here to make this ring, and that's where this word annulation comes from. So I know that was a bit brief. I'll post a screencast showing the actual mechanistic steps today or tomorrow at some point. But now we're pretty much out of time. If you have questions, again, shoot me an email either through the regular USM email or through Canvas, and I'll post further instructions about the exam on Monday. But please try to get to work on your homework 8, quiz 3, and homework bonus, or exam 3 bonus, excuse me, on Wiley Plus. So with that, we'll go ahead and wrap up this live stream, and I'll post this to YouTube in a couple hours after it renders. So we're signing off, so take care.